Let me show you how to solve pair production problems. These are not terribly difficult. Okay, again, pair production is where we've got a photon, a light particle. Okay, if it passes near a massive object like a nucleus, it's possible, both energy-wise and momentum-wise, for this photon to spawn a matter particle. So this is matter. This is a regular electron, right? And an antimatter particle. And this is, our first encounter with an antimatter particle. This is called a positron, and it's just an antimatter electron. All particles, well, a lot of particles have an antimatter particle. Some of them we say that they are their own antimatter particle. So this guy is, let's hit the right arrow here. So that guy's an electron. It's got this mass, right? That's a positron. It's got the same mass. It just has a different charge, okay? And they have different, like this guy has negative lepton numbers, et cetera, et cetera. And when we get to particle physics, we can look at antiparticles more closely. Okay, let's just do an example here. These are really pretty simple problems. Okay, so what energy in MeV is needed to create an electron-positron pair, each with a kinetic energy of 0.34 MeV? What is the wavelength of that photon? Uh-oh, you don't have the answer for wavelength. You do have the answer for this, though. Okay, it's going to be a heck of a small wavelength, right? Because it's got a ton of energy. So basically, the budget for creating this, right, is if you look, here are the masses of the electron, right? Notice how they give you the mass of the electron in MeV. What that means is that if we turn the electron into pure energy, that's how much energy it takes, right? So half a million electron volts, basically, right? So this is our budget. To create a electron takes 0.511 MeV, right? To create the positron is 0.511 MeV. So here's our E minus, here's our E plus. That's a positron there, right? And then they each have to have the same kinetic energy. Otherwise, momentum would not be conserved. So 0.34 and 0.34. And this is the kinetic energy for the electron, and this is the kinetic energy for the positron. Now, this is very complicated. I must add those together. Okay, here we go. No matrices required for this. So 0.511 plus 0.511 plus, whoops, I just said times, plus 2 times 0.34. Aha. Is 1.7702 million electron volts. That's the energy that photon must possess. Now, to figure out the wavelength of it, right, it's 1.702 times 10 to the 6th electron volts, right? So remember that 1 MeV is 1 times 10 to the 6th EV, right? Okay, so I'm going to do that times 1.602 times 10 to the minus 19th, and now I'll have joules. This is EV per joule, or joules per EV, sorry. All right, so I'm going to go that guy, this guy, times 10 to the 6th, times 1.602 E minus 19. And as far as joules go, I get that it's 2.7266 times 10 to the minus 13th joules. And then I know that that the energy is hc over lambda, so therefore lambda is hc over E, right? So that's going to be 6.626 times 10 to the minus 34. That's joule seconds, right? C is 3.00 times 10 to the 8th meters per second, right? And then the energy is going to be 2.7266 times 10 to the minus 13th joules. What do we end up with? Let's see, seconds cancel, joules cancel. So we end up with meters, which is, of course, what wavelength should be in. Okay, so here we go. So 6.626 E minus 34 times 3 E8 divided by the answer I just got. And the wavelength of this is, it's the killer photon, 7.29 times 10 to the minus 13th meters. Look out for that photon, baby. Okay. All right. So there it is, right? So basically you just have to create the matter particle, the antimatter particle. You have to give them kinetic energy, add all that together. That gives you the total energy needed, right? Just simple conservation of energy. Now the nucleus past which this photon went to create this carries some insignificant amount of energy. So certainly the energy may be just a little less than that. But anyway, let's look at the next example here. There we go. All right, so this is just exactly the opposite of that, right? So we're gonna do our photon math first and figure out the energy of this, and then we're going to figure out the energy, the kinetic energy of each particle. So let's do this. First thing is let's take this photon and figure out how many MeV it's got, right? Okay. So energy is hc over lambda, so it's going to be 6.626 minus 34 times 3e8 divided by, and this is nanometers, right? So 0.00025 times 10 to the minus 9th, right? So that is 10 to the minus 10th, 11th, 12th, 13th, right? Okay. There we go. Okay, so let's do this guy. And this will be joules, right? So 6.626 E minus 34 times 3 E8 divided by 0.00025 E minus 9. And this is 7.9512 times 10 to the minus 13th joules, right? Okay, so now we got to turn that into, let's turn it into electron volts. So 7.9512 times 10 to the minus 13th joules divided by 1.602. And this is, what is this? This is joules per electron volt. Okay, so divide that by 1.602 E minus 19. And I get just this big number, very unhelpful. So I get 4963.295.88 approximately EV, right? This is, let's put commas in there. Okay, so it's basically 4.963 MeV, right? Okay, so I'm gonna go ahead and divide that by 1e6. Okay, and that'll give me how many MeV it is. So divided by 1e6, and I get 4.963. So that equals, and there's a bunch of change, right? Okay, so now I've got how many MeV it is, right? So remember that an MeV is 1 times 10 to the 6th, right? 1 MeV is 1 times 10 to the 6th EV. That's what, like, people forget that. It's just a factor of a million, you know, right? All right, so now we've got this budget, right? We've got to create an electron-positron pair, right? They both have that much energy. So we got 0.511 spent to make our electron, 0.511 spent to make our positron, right? And then we've got Ke for the electron, Ke for the positron. And all of that's going to add up to 4.963. So this is fairly simple math. Actually, this is very complicated, right? All right, so I'm going to take 4.963 minus these guys, right? Minus 2 times 0.511. And I've got 3.941 left over for the kinetic energy. And I'm going to divide that by 2. And I got 1.97, so the kinetic energy for each of them is 1.97 MeV. All right, there you go.